I'd like to look at the integral from 1 to 2 of the integral from 0 to pi of y times sine of xy dy dx. Now, remember the outer integral corresponds to the outer differential, so that since this ends with a dx, x is the thing that goes from 1 to 2, and y is the coordinate that goes from 0 to pi, right? Okay, so we should, at least as written, focus on the inner integral. So we should do the dy integral first, meaning treat y like a variable, treat x like a constant. I'm going to just mention right now that this one is kind of involved. And what I'd like to do, I mean, even as involved as it is, I'd still like to try to go through most of the steps without doing too much. I think sometimes with too much, this will just get so messy. So I apologize a little bit that this is summarized, but I think the summary of this is going to be a little better than trying to do every last step here. So it's involved enough that I actually would like to look at the indefinite integral off to the side. So just the integral of, without the numbers listed, of y times sine of, why is there a comma there? This should just be integral of y times sine of xy dy. Apologies about the comma. Okay, since this integral ends dy, we should think of y as a variable, x as a constant, and we're actually going to integrate by parts. So with u equal y and dv equal to sine of xy dy, we should differentiate u, right, and anti-differentiate v, again with respect to y. So du is equal to 1 dy, and v to get v, so to do an integral of sine of xy with respect to y is going to actually require its own off to the side substitution. I even hesitate to call it a u substitution because we already used up u. But without showing those details, you ought to get negative 1 over x times cosine of xy. Whew. All right, so then applying integration by parts, again, apologies for the comma here, this indefinite integral should be u times v, yeah, so negative y over x times cosine of xy, plus, uv minus v du, right, minus integral v du. So v du, let's see, there's v, there's du here. With the minus sign, that's why there's a plus here, right, because it's minus minus. Integral 1 over x cosine of x dy. Okay, well, this still looks messy, but really the key thing to say here is that this integral looks relatively about as messy as y times sine of xy dy is. Actually, it's going to be considered a little easier because, remember, y is the variable, so x is a constant, and so 1 over x is a constant. Okay, so here, if we, let's see, take a look at this, we just actually took this and I think just rewrote it here. What we'll notice is that, okay, first term, copy it. And then this, oh, I see, there is a little difference here. Let's just go back. This 1 over x, yeah, that's exactly what I was saying. Y is the variable, x is constant, 1 over x is constant. Just bring this 1 over x in front of the integral. Just like if it said 5 times cosine of xy, you'd bring the 5 in front of the integral. Now the point is we need to focus on anti-differentiating cosine of xy with respect to y. That is itself its own little u substitution problem. So copy the first term, yeah, negative y over x cosine of xy, plus copy the 1 over x, and then from the substitution, there's going to be another 1 over x, and then there'll be a times sine of xy. Oh yeah, now that we're done with the integration plus c. So a lot happened here. This was an integration by parts, and along the way, there were 2 u substitutions done as well. Okay. Now if we go back to the inner definite integral, so the integral from 0 to pi, since we worked out this antiderivative rule right here, now we can go ahead and plug in pi everywhere here, and then plug in 0 everywhere here. And here's how this should work out if everything's plugged in okay, just keeping in mind that sine of 0 is 0, right? So you'll notice it's this thing, these two terms, leave out the plus c for a moment, is these two terms, what happens when you plug in pi? Well, when you plug in pi for y, then here's the first term. The second term, you plug in pi for y, you have sine of, what, that's going to be gone, right? And then for the next term, and then we have to plug in 0 for y, and then we'll get a thing that looks like this. Okay. well, let's see. There's, oh, no, no, let's just fix this correctly. So plugging in pi, you have this term here, and then you get this term when you plug in pi for y, you get this. The thing is, when you plug in 0 for y, then this term is gone. Yeah? So you plug in 0 for y, and um, this term is gone because its sine of 0 times whatever is 0. This term is also gone because there's a y in the numerator. So sorry for kind of the shuffling of terms, but what is written here actually does work. And then that's the outer integral done. What we can do then is now replace the inner integral with what we just got in here, right? And so we'll have the integral from 1 to 2, make that replacement. All this stuff that was here is copy pasted in here, then with a dx at the end. Let's copy this to the top of the next slide, removing zeros. We'll have to do an indefinite integral here again, really, to work out what's going on. This is actually two separate integrals to think about. It is rather involved, right, with the x in. Now that x is the variable, this is actually much more involved. And we're going to summarize a little bit the details here and say that for the first integral, you can do this by integrating by parts, and you'll get this. So if you, we're not going to focus on the second integral because it looks a little messy. The thing is, the first integral here, we had split into two separate integrals. The first integral plus this second integral, which is now written in blue, now becomes, the first integral is replaced by what we had in yellow here, plus the second integral. The reason we didn't do the second integral is because it's something super nice. We got really lucky that something nice happened. You see this blue integral already as one of the terms in yellow, but with a minus sign. So the second term in yellow cancels with the only term in blue, right? So we end up with, in the end, this indefinite integral up near the top ends up just being the first term in yellow. So negative sine of pi x over x, then a plus c. Okay, cool. So now that we've done that indefinite integral, we can go back to the definite integral right at the top of the slide and basically use this negative sine of pi x over x and plug in both 2 and 1. Okay, and even here, I mean, I just left a little bit of calculus notation. At least at this point we're done, but I hope you'd agree that the amount of integration done from like a Calc 2 class was pretty extreme in doing this problem. Yeah? Here's the thing. In order to integrate the question that we had as written, even not putting in every little itty bitty detail, it took up a lot of time. And we had to integrate by parts twice, and we had to do u substitution a total of 3 times, I think. But here's the thing, since y times sine of xy is continuous, we can apply Fubini's theorem and just swap the order of integration. So the integral sign swapped, and the dx and dy also swapped, and we should get the same final answer. And it turns out that this integral is going to be much easier to do. If you integrate with respect to x, treating y as a variable first, you actually only have to do a little u substitution in the beginning. There's no integration by parts that you have to do. This is actually much quicker. I think you should try it on your own. It's way faster. There's no integration by parts involved. It's not involved by any means. So this is, I think, sort of the power of Fubini's theorem is that, look, most of the time the types of functions we're double integrating are continuous, so you can swap things around. And so you should do so if things are going to be convenient to you. So I would just say, strategically start with the integral you have, start with the inner integral, but if something seems messy, at least consider swapping things.